Can we do more than that? Can we exclude something else? If I look at this matrix element, STF, my perturbation operator, and a single excited determinant, let's write it just IA. These are orbital index now, not state indexes, J. And then Emil says, I can write this Hamiltonian, perturbation Hamiltonian operator, instead of writing it explicitly out what is there, just write it like this. This is the full Hamiltonian minus the 0th order Hamiltonian and then Emil says quite correctly, this is STF, the full Hamiltonian, a single excited determinant. We had that last week. It has a French name. It's called the Brillouin theorem, and it's 0. As long as the orbitals we use are really canonical Hartree-Fock orbitals. They come from a diagonalized Fock matrix. So that's 0. But this term here, STF, that H0 Hamiltonian, that's the sum of all our Fock operators. I, number of electrons, IA, and both these determinants, either the Hartree-Fock determinant or single excited determinant, they are both eigenfunctions of the Hartree-Fock Hamiltonian. Because the orbitals are eigenfunctions of the Fock operators, so a product of the orbitals is going to be an eigenfunction of the sum of the Fock operators. So they are eigenfunctions. So if I let them act either this way or that way, I'm going to get the eigenvalue and going to get the function back. But those two are orthogonal. Those two are two different Slater determinants with different orbitals in there. Slater-Condon rules, they are 0. So this I could write as minus and then let it act to the right. I'll let it act to the left, it's easier. Let it act to the left, then I get the sum over this act on that. That's the sum over all orbital energies of the occupied orbitals. And then I get STF and this one, but these are two different Slater determinants and they overlap is 0. The whole thing is 0. So the single excited determinants don't contribute. The only thing we have is double excited determinants.